All right, welcome to The Explainer. Today, we're jumping into the science of how we build our world to stand up to one of nature's most powerful and unpredictable forces, the wind. From the tallest skyscrapers to the very roof over your head, there is a constant, invisible battle going on, and engineers are right there on the front lines.
You know, this quote just nails it, doesn't it? Wind has this beneficial side. It gives us clean energy, it cools us down, but it's also a parasite, pushing and pulling with immense unseen force on everything we build. And that parasitic side is what keeps engineers up at night.
And that destructive side, it's getting so much more expensive. Just look at these numbers. Back in the 1960s, the total economic damage from natural disasters was about $42 billion. Now, you fast forward just 3 decades to the 90s, and that number explodes to over $418 billion. That's almost a tenfold increase, and a huge chunk of that is driven by wind damage. So what's going on here?
Well, for one thing, it's the sheer number of these monster storms. On average, around 80 cyclones, you might know them as hurricanes or typhoons, they form around the world every single year. And as our cities get more and more crowded, each one of those storms has more to destroy, making the threat bigger and bigger. So that brings up a really big question for engineers. I mean, we're pretty good at designing for gravity, right? It's constant, it's predictable, it always pulls straight down. But wind, something we feel every single day, why is it such an incredibly complex challenge for architects and builders? Okay, let's get into it. The answer really comes down to the messy, chaotic, just unruly personality of wind itself. It's not some simple, straightforward force. It's more like an invisible bully. And the key word here is turbulence. See, the wind out in the real world isn't a nice, smooth river of air. Scientists call it a randomly varying dynamic phenomenon, which is really just a fancy way of saying it's a mess of chaotic, swirling eddies and totally unpredictable gusts. And that chaos makes it pretty much impossible to perfectly predict with math alone. And this analogy, it's perfect. Imagine a smooth, predictable wind flow. That's like people in an orderly line. Easy. But real-world turbulent wind is like a chaotic crowd pushing and shoving. You have no idea which way any one person is going to move next, and it's the same with any single gust of wind. And what makes it even trickier is that everything the wind bumps into changes its behavior. The friction from a city full of buildings, the smoothness of the open sea, nearby hills and valleys, even the shape of the building it's about to slam into, all of it makes the chaos even more complex. So if you can't just plug this into a neat mathematical formula, and the real world is just too complicated, how in the world do engineers figure out how to design a building so it doesn't get knocked over in a storm? Well, the answer is actually kind of brilliant in its simplicity. They build a special kind of lab, and they fight wind with more wind. They basically create their own tiny controlled storms. The number one tool in a wind engineer's kit is something called the boundary layer wind tunnel. The best way to think of it is as a giant, super sophisticated scientific wind machine. It's where they can create their own miniature, perfectly controlled storms to see how their designs hold up. Okay, so here's how they do it. First, they build these incredible, detailed, miniature models of whatever they're testing. A skyscraper, a bridge, you name it. Then they stick that model inside the tunnel, they crank up the fans to create a realistic, turbulent wind, and they cover the model with hundreds of tiny sensors to measure every little push, pull, and vibration. Now, for a long time, this was a huge blind spot. Engineers would use wind tunnels that created smooth, unrealistic wind. But then came this game-changing discovery in 1958 by Martin Jensen. He proved that to get results you can actually trust, you have to simulate the messy, turbulent wind you find in the real world's boundary layer, which is just the layer of air closest to the ground. That discovery changed everything. But here's the thing. Taming the wind isn't a one-size-fits-all kind of problem. A tall, skinny skyscraper and a low-to-the-ground suburban house face totally different kinds of threats, even from the exact same storm. And the way wind attacks these two types of buildings? It's like night and day. For a tall, flexible skyscraper, the big danger is vibration. The wind can make it sway back and forth like a giant tuning fork, which can cause serious damage over time. But for a low-rise building like a house, the number one danger is suction. The wind literally acts like a giant vacuum cleaner trying to rip the roof right off. And this right here, this is one of the most important things they've learned from all this research. The most powerful, damaging forces on a house aren't from the wind pushing against a wall. It's from suction. Think of the corners and edges of your roof. They act kind of like an airplane wing.
When wind rushes over them, it creates lift, or suction, and that force can be way stronger than the direct pressure of the wind. That's why you see roofs get peeled back starting at the corners after a big storm.
Now, even with all this amazing technology and knowledge, our understanding is far from perfect. There are still these gaps, these humbling gray areas, as the experts call them, where our theories just don't quite capture the full, raw power of nature.
I mean, listen to this. This is a pretty sobering thought from one of the pioneers in the field, Martin Jensen. He pointed out that we have very, very little data confirming that what happens to a little model in a wind tunnel is exactly what happens to a full-size building in a real hurricane. We have to rely on the models, but we can't be 100% certain they're perfect.
And these missing links, they cover some really big stuff. We still don't have a complete picture of what the wind is doing inside a tornado. We know that complex terrain, like mountains, can boost wind forces on something like a bridge by 40% or even more, but it's really hard to predict exactly how. And we're still trying to figure out if the forces really do scale up perfectly from a tiny model to the real thing.
And this, of course, is the ultimate cautionary tale for any wind engineer. Back in 1940, the Tacoma Narrows Bridge, they called it Galloping Gertie. It literally tore itself to pieces in what seemed like just a moderate wind. That dramatic collapse was a terrifying reminder that our theories aren't always enough, and underestimating the complex power of the wind can have sudden, catastrophic results. Which really just leaves us with a final urgent thought. We know so much more about wind than we ever have before, but this battle is far from over. In a world with a changing climate and the real possibility of stronger and more frequent storms, the work of understanding this invisible enemy has never been more critical. The question isn't just if the wind will blow, but are we truly ready for it when it does?